Welcome, everyone. It's a pleasure to be here and to talk about challenges and opportunities for characterization of fine particulate matter indoors in the frame of the 15th webinar of the Brazilian Journal of Analytical Chemistry. Why it's important to study indoor air quality. Indoor air quality, it's a hot topic nowadays due to the global warming, because global warming has led to the development of energy-saving buildings, which are characterized by low exchange rate, air exchange rate. And the other big problem is why do we have these type of energy-saving buildings? Because people nowadays spend more than 90% of their lives indoors. And because of working, because of commuting, because of living. And this is why the number of the articles dealing with indoor air quality has significantly increased, and the main investigated places are dwellings, schools, universities, museums, and hospitals. I hope that the slide change it's working. No? So now I'm on the third slide. Please tell me if it's frozen. If we look at the indoor air pollution sources, we can see, we can appreciate from this slide that this is a quite complex issue. So the type of pollutants, of course, can be gaseous, inorganic, organic, or the pollutant can be also particulate matter. And also the profile of the pollutants and the sources will depend a lot on the indoor environment. And in a house, for example, in a dwelling, so what we have, we have kitchen, living room, bathroom, bedroom, and we have to take into consideration if it's workplace, like an office, we have other sources like electronic devices, office supplies, and further on. If you would like to characterize, to classify the air pollutants, we can classify them according to the source, the mode of release, and the chemical composition and size. If we are looking at the sources, we can say that we have primary air pollutants, which are originating from direct emission into atmosphere, or we have secondary air pollutants due to the reaction with an atmospheric pollutant, namely ozone or nitrogen oxides. If we are looking at the mode of release, we are talking of indoor air pollution or outdoor air pollution, and we can see that their profile is different. For example, indoor air pollution arises mainly because of activities such as cooking, less smoking, and air conditioning, while in the case of outdoor air pollutants, the main source is the industrial activity and transportation. If you look at the chemical composition and size, we can say that we have, as I mentioned before, gaseous air pollutants, inorganic, organic, and particulate matter, which are solid or liquid aerosols. But the problem is even more complex if we try to go in depth. So for example, in the case of primary sources, the primary sources can, as I said, be due to indoor emission for activities such as building material, furnishings, cleaning activity, combustion from cigarette smoking, gas stoves, incense or candle burning. Then we have also activities such as cooking. And please do not forget that humans, our skin, our clothes, can also be a source of a primary indoor air pollutants. And of course, is a huge topic also, the indoor air pollution due to microbes. And another part of the primary sources is due to infiltration of the outdoor air pollutants into indoors, but we have to think not only of ozone or nitrogen oxide, but also of mineral dust. As regarding the composition, you can see that there are a myriad of chemical compounds that that can be identified or determined in indoor environment. For example, we have volatile organic compounds, chlorinated molecules, amines and phthalates, cholesterols, a lot of compounds. So there's a lot of work to be done. If we are looking to the secondary sources, as I told you, it's mainly due to a chemical reaction. The chemical reaction can be an addition with chlorine or chlorination, or because of the bleaching because of the detergent use and so on. Then we have nitrosation with nitrous acid in the indoor air community. It's called HONO. And we have also reactions between ozone and already formed indoor air pollutants. And usually there is a difference made between ozonolysis, which leads to the formation of Cree intermediates like carbonyls, carboxylic acids, secondary ozonides, hydroperoxide esters. And also another part of the oxidation with ozone does not involve ozonolysis, like, for example, reaction between cooking oils with ozone, or the skin oil that we have on our skin, terpenes, or polyaromatic hydrocarbons. Also to this category belongs the photodegradation and photolysis, which involves mainly surfaces. It's again a very, very complex issue. As I told you, that it's important to take into consideration the human, the building material, all the surfaces that can act as sink, or they can also release or pollutants, or on the surfaces can happen chemical reaction. And we also have mechanical processes like human walking or airflow leading to generation or a suspension of dust carpet fibers. The topic of my presentation is mainly determination of particulate matter. I like very much this figure on the particulate matter because it shows how tiny are these particulate matters in comparison with the human hair. And we know that, again, we are talking about aerosols. We can talk about condensation aerosols, dispersion aerosols, fog, haze, mist, smoke. So it's very, very complicated. And according to the size, usually we say that atmospheric aerosols are liquid or solid particles, as I mentioned before, which have a diameter less than 100 micrometer. But the most important, the most dangerous are those particles, especially which are less than 10 micrometer in diameter, because these particles can enter directly into our bloodstream, can enter into the lymphatic system and to the lungs, and from there they can be transported directly to other organs because of their high solubility. And the focus in the previous years was mainly on the determination of PM10, where the aerodynamic diameter of the particle is less than 10 micrometers. But nowadays, the focus is mainly on PM2.5. You can see it's even more dangerous than the PM10. And if we are looking at the chemical composition of the aerosols, it's again a very, very complex issue. So we have carbonaceous materials, we have metallic oxides, glasses, inorganic anions, which all influences the composition. Then we have a lot of processes like coagulation, diffusion, the reaction, the scavenging with precipitation. After coagulation, the bigger particle can undergo to sedimentation. So again, this is a very complex issue that has to be taken into consideration when someone would like to deal with PM analysis. And I don't know what's the situation in Brazil, but in Hungary we had several severe problems with asbestos and with radon, which nowadays hopefully has been solved, but it was also a very, very serious problem in the 80s. And if we are looking at the composition of inorganic particles, so again, we are looking at the element side, so we can detect elements which are originating like aluminum, iron, calcium, silicon, which are originating from soil erosion, rock dust, coal combustion. We have also marine aerosols. Again, the PM composition in cities next to the oceans, next to the sea, is completely different from the landlocked countries, like, for example, in Hungary. Then we have a lot of elements which were introduced by human activities. And then, as I told you, the problem is that due to the condensation of water, other changes can occur. For example, atmospheric ammonia as pollutant will be converted into ammonium. Nitrogen oxide will be nitrogen dioxide will be disproportionating. One of the products is nitrate, or from the elements introduced by human activities. From bromine, we get hydrogen bromide. From chloride, HCl. From again, we get from sulfur sulfate or sulfide. So it's very, very complex issue, but it's good to know in order if someone would like to perform source apportionment after the measurements. The organic issue, it's even more complex. We have several compounds. We have neutral ones like hydrocarbons or polyaromatic hydrocarbons. We have neutral compounds which are oxygenated like aldehydes, epoxides, peroxides, esters, quinone, lactones, and so on. But also we have acidic and basic or alkaline groups. For example, acidic are fatty acids, phenols, and from the alkaline compounds, I have to mention the acridine, which is an irritant. A very important topic is to determine the polycyclic aromatic hydrocarbons, which can be on the surface of the particulate matter. So, they can also be along. The more volatile ones can be also present in the atmosphere. So we have particle-bound and atmospheric polyaromatic hydrocarbons, which are usually originating from the incomplete combustion of engines from vehicles, and they are highly carcinogenic. Why? So I think that I have already convinced you why it's important to perform indoor air quality studies, mainly because these indoor air pollutants are exerting an adverse health effect. These adverse health effects can be cardiovascular diseases. These indoor air pollutants can cause respiratory tract diseases or irritation, for example, eye irritation. And there were also some studies where the volatile organic compound concentration in the indoor air or on the surface of the particles and lung cancer. So I think that is infographic. It's quite expressive. It's in the terms that the indoor air quality can be from 2 to 5 times worse than outdoor air quality. The US Environmental Protection Agency ranked several indoor air pollutants in the top 5 of their environmental risk list. And we can see that the number of the diseases, the illnesses can increase substantially in the case of indoor air pollution. That's why I think it's an important topic that I think that it will gain more importance in the future. If we are looking now at the PM 2.5 studies, we can also say that the number of the studies dealing with this topic has substantially increased in the past decades, and it will gain again more and more importance as the number of these buildings with mechanical ventilation or air conditioning will also increase, is expected to increase in the future. If somebody would like to sample particulate matter, he or she has to take into consideration that the build-up is again quite complex. Usually we have a press separator, we have to use a filter onto which to sample the particulate matter. We have with a certain flow rate that should be controlled by using an airflow meter. We have a lot of tubing and sampling pumps. Again, everything is dependent on the flow rate to have a membrane pump or a rotary vacuum pump. Concerning the filter media, the most popular filters are the Teflon and the quartz fiber filters. And the biggest problem is that also you can see from this last column on application that there is no unique filter that is suitable for all what we would like to determine. So first of all, the mass concentration, or the elements, the inorganic or organic ions, the organic compounds, or the elemental carbon. So because of the nature of these filters. So as I mentioned, the most popular are the quartz fiber filter, which is good for organic carbon, for elemental carbon analysis, but Teflon is much better for elemental analysis. And due to the fact that the quartz fiber filter samples have quite high blend values for several elements. Of course, these filters, again, should have a low hygroscopicity. They should have a high efficiency, and for the collection of PM, and to be mechanically and thermally stable, and of course chemically inert. Again, the next topic is then, okay, we know that we would like to determine PM, we would like to determine the components in the particulate matter. We know that it is better to determine the PM 2.5, but always the goal is to protect human health. And to protect human health, it means that all my measurements should be oriented towards the assessment of the human exposure. For this, there are several approaches. For example, the direct measurements, when it's made directly on a person. No, we put the samplers, especially close to the breathing zone. Okay, there are also the biological monitoring, which is not topic of this presentation, which is also very important. And there are the indirect methods, usually the fixed stations, measurements using fixed stations, indoors and of course outdoor. And what's the problem? The problem is that if we would like to use the direct measurements, we need a lot of time, a lot of money, a lot of individuals that are willing to do it on a voluntary basis. And it's not always easy because we interfere with the daily routine of the person. So that's why usually what we do is that we prefer to do fixed sampling campaigns, fixed sampling or fixed measurements, fixed station measurements, of course. And then we have to take into consideration how to do an extrapolation of the results obtained in this case, because it depends, of course, on the distance of where is put the sampler, the fixed sampler, in comparison with the human, or where is the indoor air pollution source, or how much time do we do this, because it's also a question on exposure. And usually the urban background monitoring stations are not suitable, the outdoor urban monitoring stations, to retrieve data and to estimate the human exposure, because they are usually not very precise from this point of view. Of course, that if we would like to do a sampling campaign, like also in my life, what we did not want to focus only on the PM. So we would like to have multi-component analysis. So if somebody has the time, the money, and all the willingness, then we would like to determine a lot of compounds. And these slides only want to illustrate that these measurements can be done in continuous mode, or in time integrated mode. And this means, for example, that in time integrated, if you look at the NO2, nitrogen dioxide, it can be determined in form of chemi-adsorption, for example, as nitrite ion, and to be converted into reddish purple azodide, which can be spectrophotometrically, UV photometrically determined. Or there's the possibility, if we have already the nitrite or nitrate ion, to be determined by ion chromatography. For ozone, we also have, in the case of time-integrated analysis, a diffusive way, and then subsequent ozonolysis and condensation to form an azide, which can be determined by UV spectrophotometry. And if somebody would like to determine VOCs and carbonyls, there are also the possibilities to have time-integrated data by either passive sampling, when the diffusive body is placed into a sampling point, and after a certain time, certain amount of days, number of days, can be collected back and extracted. In the case of VOCs, we can use thermal desorption. In the case of carbonyls, we can extract in a solvent the compounds. But we always have the possibility of active sampling by using pumps, which again, if it's done at home or at the workplace, it's bothering the people because of the noise that the pumps are making, because then air is filtered through cartridges. Otherwise, also those cartridges should be also extracted further on. In the case of volatile compounds, we have the possibility to use gas chromatography, nowadays usually coupled to a mass spectrometer, or in the case of non-volatile carbonyls, for example, to use HPLC, high-performance liquid chromatography, normally coupled to a UV detector. In the case of continuous measurements, for example, what is widespread nowadays is cavity ring-down spectroscopy for several inorganic air pollutants. For NO2, we have also the chemiluminescence, and for the organic ones, for example, VOCs, we have the proton transfer reaction mass spectrometer, which is quite a quite expensive technique. And by the way, these instruments are very difficult to be placed on a sampling site. So usually it is not used in dwellings, in schools or kindergartens. Maybe so far these type of measurements are still under consideration, are mainly used in research. So as I told you that we would like to have a multi-pollutant, perform a multi-pollutant analysis, also in the case of PM. So not only gaseous contaminants, inorganic, organic, but also for PM, we would like to get as much information as possible. So for example, I mean, the minimum thing is to determine the mass concentration. This can be determined in real time by using optical light scattering, number of concentration, again, in real time, direct measurements. Then mass concentrations, what we use normally is time integrated. It's much cheaper. In this case, we have the filters onto which the PM was collected. And then the PM, the mass concentration is determined through weighing on a microbalance in a climatic chamber. The problem is, especially if it's an indoor PM sample, is that the resolution of the microbalance should be around 1 microgram. And the problem is that also the relative humidity should be very strictly controlled. So I had the privilege to do this type of measurements, and it's a quite strict protocol to let them filter into the climatic chamber for about 48 hours to get the relative humidity there, absorb the relative humidity there, then to weigh, then to close, to perform the sampling. And then again, after sampling, the loaded filters are again placed into the climatic chamber, and the weighing will start only after 48 hours after they have the same relative humidity as before, because we are talking about micrograms. If we are lucky, we are talking about 100, from 100 micrograms and above, if not even less. What would like to do, as we could see that there are several organic compounds not only in the gaseous phase, but also in the case of the filter. So it means that we cannot determine all the organic compounds. Sometimes if you want to have a quick result, what we are focusing on is the organic compound, organic content, and the elemental organic carbon or elemental carbon of the sample. For that, there are some special instruments, thermal optical transmission instruments available in some research institutes across Europe, and at least to get some information on the organic compound if we cannot do the determination of the individual. Not because of, sometimes not, it's not because of a question of finance, it's a question also that the sample amount is limited, and how to extract and how to get the information from these tiny amounts of filter materials. Then, of course, one of the aspects in the case of the multi-pollutant analysis in indoor particulate matter is the determination of elements. For that, usually ICP is used, at a lesser extent X-ray fluorescence. As I mentioned, the major ions in time-integrated mode can be determined by ion chromatography, and if the focus is on the VOCs, then GCMS, LCMS can be used after thermal desorption, again, which is again not common in the laboratories to have this type of units installed, equipped with the GC instruments. Another interesting topic is again that not to perform only chemical analysis to know what is the concentration of the elements, what is the concentration of the organic compound. Always try to link the results with the human exposure, with human health. And one of the things that is also important in the case of these PM samples is their oxidative potential. So usually when these very tiny particles are inhaled and they are penetrating until the lungs. So what they need is the respiratory tract lining fluid. So usually this is not dry. If we had dry esophagus, dry throat, we know what happens. It hurts. So usually all our lung surface and these respiratory tract is covered by respiratory tract lining fluid, which contains antioxidants such as ascorbate, urate, glutathione, and they are acting against inflammation, tissue injury, protein lipid oxidation. And it would be nice also to be able to determine not only the chemical composition of the particulate matter, but also to link it with the oxidative potential, if they are responsible, also which components of the PM are responsible for the inflammations, for the adverse health effects. And for these two types of measurements or approaches have been developed. One is the acellular, the cell-free, and the cellular one. In the case of acellular, we have to distinguish between those which are suitable, for example, only for radicals, like the electron spin resonance or fluorescence-based techniques. What is much more common is to use the depletion of these antioxidants. So it means that usually adequate portions of the PM samples are incubated with this respiratory tract fluid, for example, containing glutathione, ascorbate, dithiothreitol in a certain concentration, and then to see after the incubation of 4 or 5 hours or 1 day, depends on the protocol, to see how much remain from these antioxidants. So what to do, what to have? Of course, that it would be nice to use direct measurements instruments, and especially, I don't know in Brazil, but in Europe, the European Commission favors nowadays a lot what is called citizen science, to empower, to involve the society, the members of the society into science. And one of the suitable things is that to operate with these direct measurement instruments, which are small, which can be instructed. They don't have to have necessarily chemical knowledge or knowledge on chemistry, and to be able to use it. And one of the biggest direction now in this indoor air research is the development of sensors. So here you can see some examples for direct measurements for example, for ultrafine particles, which are also very, very harmful. Carbon monoxide based on the electrochemical sensor, CO2, which is the CO2 direct measurement instrument is based on infrared absorption. What's the advantage from a chemical point of view, from a scientific point of view, is also that we can register peaks, short-term peaks of this indoor air, while in the case of time-integrated, either passive or active sampling, what is obtained is a mean value. So it's also, for our point of view, this is important to perform direct measurements. From this point of view, we have also several small equipment for ozone measurements. You can see here the personal monitoring for ozone, or one based on semiconductor sensor. And for NO2, formaldehyde, total volatile organic compounds, also we have several sensors developed. And a big problem is with these sensors and this is why the efforts are made now, how to develop to these sensors to give from lot to lot, good results. The calibration of the sensors, it's a problematic issue, especially for those small ones, because these are instruments. What I showed this in this case, the situation is much more better. So as a chemist, what I prefer, to be honest, is much more either a passive sampler or an active sampler, for example, like we use for VOCs or for aldehydes. And if this is not enough, so there are still other factors to be taken into consideration when doing a campaign, a sampling campaign. Would you like to get information? So don't forget that we always have to register the temperature, the relative humidity, and the light intensity. In the case of buildings with ventilation, we use an anemometer normally. And then what we always take into consideration is, if we would like to determine the human exposure, to place all the instruments relatively at the breathing zone of an average height person. And if you want more complicated thing, is that usually we prepare a checklist before going to the sampling and choosing the sampling location with a lot of technical data on the number of occupants, surface, type of windows, number of windows, and ventilation, and so on. And also during the sampling campaigns, we usually ask the volunteers that are present to keep a diary of their activities. And if you want to make even more complicated the things, because I said at the beginning that the indoor air quality is always depending on the outdoor air quality. So usually concomitant outdoor sampling of either PM or the organic or gaseous inorganic pollutants should be performed. Usually indoor-outdoor ratios are also calculated. So as I mentioned, there were several projects financed by the European Commission on indoor air. You can see there were about 12 starting from 1992. I had the privilege to participate into the AirMax project, not only as helping in Hungary to perform sampling, not officially. And officially, I could also join the officer project as an official partner, and when our laboratory was responsible for the determination of ozone and nitrogen dioxide in all of the sampling locations, and we also had all responsibility on the particulate matter determination. Here on this map, you can see the countries where sampling was performed. So because there were 13 institutes involved in this project, but not in every country sampling was performed. And the focus was on offices, especially on mechanically ventilated, so air-conditioned equipped offices. So what I told you, you can see that the last project, that's finished in 2013. Of course, we also asked for an extension because it was such a demanding project. Usually, European Commission gives a half a year, 1 year prolongation, extension of the project. And then by publishing everything, I think that we have finished publishing. Even last year, one of the research groups published results based on this project. So it was a huge project. It was also a huge success. I'm proud of having been part of that project. And what you can see, I cannot show you since then other project. It's not because I am lazy or I could not find it. I stopped this search. It's because the fact that after the Euro Officer project was told that by the European Commission that these indoor air projects will be now a little bit put aside. There are other priorities for the European Commission, which is understandable. And this year they start, last year there was in the frame of the new budget, new European Commission budget was also launched an application for indoor air project. But finally, one project was granted, and that is dealing with sensors. What I told you, because the European Commission focuses a lot on the citizen science and on these sensor issue, because these sensors can be better used even by society members who are not trained in chemistry or indoor air or outdoor air chemistry. So if you would like to little bit to see what were these projects dealing with, they were dealing usually with particulate matter analysis, PM10, PM2.5, ultrafine particles. Also, there were a lot of focus on inorganic gaseous contaminants and organic ones. So here you can see that what classes were determined. And in the case of officer, if you are looking at the PM, in the case of officer, the PM analysis focused on, of course, gravimetric analysis, which is a must in all cases. I told you with the microbalance measurements. And we focused on elemental characterization, mainly by inductively coupled plasma sector field mass spectrometer after microwave-assisted aquaregia digestion. But we also always keeping in mind this human exposure, this human health. We performed on part of the PM samples water-soluble fraction analysis, inorganic ions, and also elements. And because of the fact that these filters, which had around between 37 and 47 millimeter diameter, and it's finite, so it's not infinite. So it means that we focused from the point of view of organic contaminants on the elimination of organic carbon, and parallel, because it's always interesting to get the elemental carbon. You know, the difference is that in the case of organic carbon, the PM sample is combusted in the presence of helium and helium, while in the case of elemental carbon, also in presence of oxygen. So this is how discrimination can be made. Then this carbon dioxide is converted into methane, and it's determined by flame ionization detector. And what was key, because this project because of the health aspects, the human exposure, is to determine the oxidative potential and to link it with the different components. So that's why it was a crucial point of this project, because we know that that not all the filtered materials are suitable for each type of measurement. This is a dream, but it's unfortunately not true. So let us see. I would like to show you one part of the work which was performed in Hungary. We evaluated about 20 office buildings, But of course, the measurements, to carry out measurements, it's very, very expensive to carry out in, by the way, in 2 seasons, in summer, and because there's also seasonal variation, summer and winter season. So based on the further preliminary evaluation, just done with a lot of checklist work, with also with the evaluation of the health status of the volunteers. We chose 5 buildings, 5 office buildings equipped with air conditioning. It is alongside the Danube River and characterized by medium and high intensity, but not heavy one, and not so heavy one. And the first thing what was surprising is when we determined the mass concentration, indoor and outdoors. I always mentioned you that we cannot perform indoor measurements without outdoor ones. So in the case of this, because of the focus was to analyze, to get data from buildings equipped with mechanical ventilation, preferably air conditioning, so we had to place the PM sampler next to the air intake outside. And inside, you can see we tried to insulate the sampler because it was a quite noisy one. This is another big problem, how to, if you would like to have a sufficient amount of PM sample, how to do the insulation, how to not disturb the everyday life or the working life of the work of the employees there. And it was surprising that if you look at this plot, that we plotted the outdoor PM 2.5 mass concentration, a microgram per cubic meter of air filtered or sampled as a function of the indoor PM 2.5 mass concentration, you can see that okay, from indoor point of view, there is no uniform regulation across Europe. So usually say that the 15 microgram per cubic meter is something which below it's adequate. So in this case, the indoor air PM 2.5 mass concentrations were quite adequate. But if you look at the outdoor ones, it's scaring because several passed. There are 2 values. For example, if you take the World Health Organization guideline, it's not obligatory, but guideline values. At that time of this project, the annual guideline value was 10 microgram per cubic meter. You see in several cases, we had higher PM 2.5 concentration for outdoor. And we had also a 25 microgram per cubic meter target value or guideline value, target value in Europe and guideline value according to the World Health Organization, which it means that for 3-4 days, there can be peaks of these 25 microgram per cubic meter values, but generally yearly on a mean basis, these should not be 10 microgram per cubic meter. But you can see that now, since September 2021, the guidelines of the WHO were decreased. Instead of 10, now is 5 the guideline value which is recommended, and instead for the peak value, instead of 25, it's 15. So if I change now this graph, the situation would be much worse. And what we were happy, for example, happy was during the pandemic. Of course, it was a very sad period in the life of everyone, but at least in terms of air pollution, in terms of atmospheric and environment pollution, we could see that several good phenomena started. But now coming back to the everyday life, we are again in a bad situation. We are again contaminating. So still in Hungary, the outdoor PM 2.5 concentration is quite high. We cannot observe these guideline values. And the problem is that in Hungary nowadays, not industrial activity is the biggest problem, but mainly the commuting, the traffic. There's a heavy traffic. Many people after the pandemic, many people do not do not use again the public means of transport. They are still using their cars, and they are still contaminating. We have several alarm issues every year in terms of PM 2.5 concentration. However, if you look if you look at these 15 value, so in many cases it was achievable. So it means that the indoor air, the air was quite well filtered. So of course, they are again in the European Commission. There is a strict regulation how to clean and to replace the filters, and that's why we can say that it was working very well. And also, if you look at the indoor-outdoor mass concentration ratio, or it was almost in all cases less than 1. It means that it's no indoor activity contributing to have a polluted environment. Only in one case we had this issue, but in that case we know that we were not allowed to place the sampler because it was noisy into the office itself. We had to put it into a place in a community place where there was a soft drink machine and dispenser machine, and there was a closed kitchen. So we think that maybe mainly the walking, what I told you, the walking, the resuspension of the dust and further erosion caused this issue to have higher indoor mass concentration than outdoor. And it was really challenging. So we tried to also to sample. We were playing. No, we could not decide at the beginning which would be good, the quartz fiber filter or the Teflon filter. So that's why we did alternately. On Mondays, Wednesdays, Fridays, we use one filter material. On the other days, the next one. And we tried to focus to do the sampling only for 8 hours. Only for 8 hours. This is the work shift in the offices. So we didn't want to go beyond. And that's why we wanted to increase the amount of the PM 2.5. That's why we have the noisy equipment and not this smaller or the lower flow rate equipment. In terms of elemental analysis, we could see that with the 8 hours, the mass was very, very little in order to perform analysis. So that's proper analysis, the wet digestion. I mean, the wet chemical analysis, the digestion with microwaves, and aquaregia. So that's why we opted for proton-induced X-ray emission. It was quite good. We got better results in the case of Teflon filter. The quartz one, because of the fact that its fibers have a certain depth, or the penetration of the proton beam was not very good. So, but you could see that in the case of Teflon, we could determine quite a lot of elements, and there were not too many differences between the indoor elemental composition of the PM and the outdoor one. And even we could identify that, for example, in one of the sampling places, it was an office where the correspondence with the clients was done, and we could clearly identify calcium carbonate, which is an additive from paper. So it was confirmed by scanning electron microscopy measurements and the corresponding X-ray fluorescence spectra. In the case of these elements, these data, we could do more and more data evaluation. For example, one of the interesting approaches is to calculate the crustal enrichment factor, which is calculated relating the elemental concentration results, to the crustal rock composition determined by Vedapol in 1995. We could do this for indoor, for outdoor concentration of elements, and usually it is believed that if this crustal enrichment factor is higher than 100, it's clearly due to anthropogenic activities between 10 and 100 both, and if it's less, crustal and non-crustal emission sources, so anthropogenic, non-anthropogenic, and less than 10, it's definitely, for example, soil, dust resuspension, and so on. And we could see here that how the lowest enrichment, crustal enrichment factor was for titanium, and then how it increased until sulfur. There were not too many differences between the red and the blue columns, which refer to the outdoor-indoor crustal enrichment factor. But if we divide them, the indoor to the outdoor, usually if we get the new enrichment factor, which is the indoor enrichment factor, was introduced by one of our colleagues at our institute, Professor Sharma. And he said that if, again, the indoor EF for an element, it's around 1, it means that there is no infiltration from outside, and I think that it can be quite nicely seen. So only for some elements have a higher indoor EF than 1, but for the maximum value. But if you look at the mean, the situation is quite good. In terms of oxidative potential, again, and this was a crucial factor in the project, because we were keen on determining this oxidative potential. We had colleagues from London, from the King's College, who were performing these measurements for the project partners. And you can see, I've told you, we had the loaded PM sample. We took out with a punch small discs, which were incubated in respiratory tract lining fluid, a synthetic one, of course. Otherwise, it could have been problems to use real ones. And what was the first experience? Because of the membrane filters, these very, very small discs rolled. And that's why the English colleagues asked us to perform the PM sampling onto quartz fiber filters, because that was much more easy to handle and to perform the incubation. What was observed? So they tried to incubate this respiratory tract lining fluid consisting of ascorbate, urate, and glutathione. Ascorbate and urate can be determined by high-performance liquid chromatography with electrochemical detection, and the glutathione by microplate reader using an enzyme-linked assay. Glutathione determination is very, very complicated. It's oxidized very easily. It interferes also with ascorbate, with other compounds. So it cannot be, by chromatographic means, it's very, very difficult to be determined. And of course, then we observe that you can see, if you look at this graph here, columns, there are no columns on urate depletion. So we started with 200 micromolar concentration of ascorbate and reduced glutathione, and urate was inert. Where was depletion was in the case of ascorbate and reduced glutathione. And this shows only this campaign, but we also showed seasonal changes on this. And what then we tried to do, it was to do a correlation study. Okay, we had the elemental concentration, and to our surprise, very little correlation was observed between the oxidative potential, the depletion rate, and the element concentration. We had 2 cases, in the case of chromium and zinc, when we got a correlation supported statistically, mathematically statistically. And I thought that in the case of glutathione mainly, yes, in the case of ascorbate, nothing. And I thought that, okay, if it's glutathione, that the correlation will be between zinc and the chalcophil element, between the sulfur and the chalcophil element, like from the zinc. But to our surprise, also chromium, which is not a chalcophil element, also showed some correlation. So this means that the issue is much more complex. And our suspicion was that mainly if there is responsible for this depletion is much more the organic compounds than the inorganic ones. And maybe this is also understandable. If you look at the chemical composition of a particulate matter, usually we know that the elemental content is about 5% or less than 5%, and the majority is organic, elemental carbon, organic carbon, and of course microorganisms also involved. Usually the results of the depletion, of the antioxidant depletion, was expressed in terms of the micrograms of the PM 2.5 collected. Other possibility is the air filtered through these 8 hours, but the proper one, which is more used for human exposure, is the to relate the depletion of the antioxidants to the mass of the PM 2.5 sample. So, and then what was missing? What was missing in this approach was the water soluble fraction. So we said that not only not all the elements which are dissolved or solubilized by microwave assisted aquaregia digestion will also penetrate into the lung. So it would have been would have been nice to go further on to develop a method including wet chemical analysis. So it means that we had to switch the strategy to switch to ICP, to switch to this water extraction. We performed with isonication. The advantage is that the cations and ions can be determined, and from the same sample, also the elements by ICP-MS. We still kept the oxidative potential. We could also keep the thermal optical transmittance measurements in order to evaluate the organic matter content, and then to see what can we get, so what information can to be obtained. And the biggest problem, because the oxidative potential measurement went very well with the quartz fiber filter sample, so we opted to do the sampling on to quartz fiber filters. And then the problem what we encountered is that the huge amount of huge concentration, blank values for aluminium, for iron, for chromium, so on. Of course, that the oxidative potential also works. Oxidative potential, the measurements work also with the Teflon, but that for full filter, not to cut discs. And we wanted to get as much information as possible. In the good news, for example, was that we also tried to check our developed method with certified reference materials. We had 2 available, and in that case, for the aquaregia and the water soluble portions, if we sum them, it was quite good for the majority of the elements. But I am highlighting only what is worse. Maybe it's not a good strategy to highlight what is not good in a work, no. But in the case of chromium, we observed some differences. From the certified value was 402, and we did not get these back. We think that there's a type of chromium oxide in this SRM, in this certified reference material, that it impeded its digestion, its solubilization or dissolution. In the case of the other certified reference material, it was interesting that we did not have this problem. And what was a big problem was antimony. Antimony chloride, the antimony 5 chloride seems that has a high volatility because what we did, I did not mention that after the microassisted digestion, what we did is still that we evaporated almost until dryness. The whole 5 milliliter of sample that we had in these quartz inlets, and then we just suspended the sample in 5% nitric acid solution for the ICP-MS measurements, and it was a problem because some elements are volatile, and now we are doing measurements with Teflon membrane sample. Also, it's the same issue for tin. So tin and antimony cannot be recuperated if you would like to apply this evaporation method. In terms of the inorganic ions, I think that we could get very good instrumental and method detection limits, good linearity, sensitivity, and we tried also to spike the sample and with the two concentration levels, like in the case of the elements, when I told you about the loss, it was checked also by spiking, but no problem. And then I would like to show only, this is the last data. So what was important? So with the 8-hour sampling, we were not capable of determining many elements. So we had to increase the sampling for 5 days. Then we could perform the sampling on quartz fiber filter samples. This is only because of the oxidative potential. Otherwise, Teflon membrane filter would be much more better. Then again, what was important, okay, the different locations not important, but we, of course, being a European Union project, we have sampling locations in Hungary, Italy, Netherlands, Athens, in Greece. The samples from France were broken. I don't know, so they had a technical issue with the mechanical rupture of the edge of the filter, so we could not analyze samples originating from France. And what we observed that it depending on the flow rate of the pump. If the flow rate was higher, so you see tolerant people in the Southern Europe, because they could support, how to say, beer with the noise of the equipment for 5 days, because in that case we could collect, or in that case sufficient amount of PM was collected, and many of 13, 14 elements out of the 15 that we could monitor by ICP, high resolution equipment that we had at that time, monitor the elements. And what we identified is that at least 400 micrograms of PM 2.5 sample is needed to get some elemental information. Otherwise, in terms of oxidative potential, OC, EC measurements, we had no problem. Always the crucial factor was the determination of elements. So in conclusion, so I would like to emphasize is that we developed a method which is suitable for multi-component analysis in PM 2.5. I mean elements by ICP-MS after microassisted digestion, aquaregia digestion, or water-soluble fraction determination of the elements is also possible. Elemental carbon, organic carbon, oxidative potential, ions, the major inorganic ions. So I think a lot of valuable data could be obtained only from one filter sample, not from different filter samples. We also emphasize the importance of the determination of the water-soluble fractions, and of course, the most critical issue was the use of the quartz fiber filter, the blank value, the high elemental blank values for the quartz fiber filters, which impeded to determine as many elements as we would have liked to determine if it were relevant. And again, the critical mass for determination to be successful, it was about 400 micrograms, which could not be achieved in each situation, not during 8 hours of sampling even with a relatively higher flow rate, applying a higher flow rate. So plans for future. So officer is already gone. We are collecting the fruits of it. So I would like to go further. I use still the network of the friends, of the colleagues that we established during the officer, and now I'm also involved in a cost action project. It's also a networking project. I met other colleagues from this community. It's also a cost action project. It's a networking project on indoor air pollution. And I would like to go further one. We have a joint venture with colleagues from Italy on indoor air quality in restaurant kitchens. A big challenge, and our ambition is now to sample only for 6 hours. Unfortunately, or fortunately for them, for the cooks, that they are not working for 8 hours. They are mainly working during 6 hours. So I think we consider to have separate sampling onto Teflon membrane or for the oxidative potential on quartz fiber fiber, but not from the same one. And the primary focus will be mainly on the organic pollutants and not on the inorganic. So the particle phase, the particle bound, and also the gas phase one, because my impression is that those 5% of element content in the PM samples, it's not responsible for, not primarily responsible for the oxidative potential of the PM sample. That's why we would like to extend the work or to focus on the organic ones. The big problem is that I am an inorganic and atomic spectrometric chemist. I wouldn't say expert. I think that I wouldn't say, even if I'm retired, I wouldn't say that I'm an expert. I think we learn every day. But I am sad because, again, I don't know why it's the situation in Brazil, but in Hungary and in Europe, there's a huge shift from the inorganic analytical chemistry to the organic one. And also this is very sad because we have those instruments like an ICP, which has to be maintained, it has to be kept alive, and I don't know why and I don't know how, because finally that what I can do is only to like an analyst to provide measurements, small analysis for in bigger project, but a huge project only on inorganic components of inorganic pollutants, not only in the case of PM, is not possible anymore. But this is what I learned and this is what I like. But of course, I am open to new challenges. So I am now diving into this organic air pollutant analysis and investigation. And thank you very much for your attention.